Yes, good afternoon to all. Am I audible?
Yes, sir.
Yes, sir.
Yes, okay. So please be maintain, keep mute mode during the class. So whenever you have queries or questions, you may post in chat box. Okay. So I'm going to share the screen. Right. Is it visible to you? Yes. Yes. Is it visible?
Yes, sir. Now it
Yes,
is
sir.
open.
Okay. Right. So just we will discuss previous class. Then let me continue. Okay. Right. So what about the previous class means? Okay. Types of the electrodes. We have discussed various type of the electrodes. That electrodes may be utilizes to measure the potential of the cell. Okay. Like hydrogen electrode, glass electrode, calomel electrode, metal ion electrode, then silver chloride electrode, then quinhydron electrode. So
Electro.
these all electrodes may use it to get the potential. With respect to that, we can find out the concentration of any electrolyte solutions that may be participated in acid-base titrations or redox titrations or precipitation titrations. Okay. So we have one practical on pH-metry and potentiometry, right? So during that time also we will discuss about the electrode construction of the electrode and utilization of the electrodes, right? So further, the continuation of the topic, that is electrode polarization, the concept of electrode polarization, right? So simply polar means that may containing partial positive charge and partial negative. So that solutions are we may called as polar solutions. So what is here polarization means? The electrode is said to be polarized. When the electrode is said to be polarized, so if we can write oxidation process, oxidation, right? So we gives rise to reductant, right? Plus n number of electrons. This is the somehow reaction, right? So means oxidation means the reductant that will give electrons. This is the oxidation process means that may releases electrons or loss of electrons. By observing that loss of electrons, that may called reduction, right? So the forward is oxidation, reverse is reduction. Therefore the overall the oxidation reduction processes are
Redox reaction.
disturbed, right? Oxidation process means simply loss of electrons, right? Reduction means gain of electrons. The
Yes,
both are takes place in a single reaction means redox reaction.
redox reaction.
That redox reaction should be disturbed by the application of external current, right? So if we can apply external current to that system, means redox reaction system, at the time, so this equilibrium position may be disturbed. So that is called polarization. What equilibrium position means? Somehow involved in oxidation, somehow involved in reduction, right? So at equilibrium position, the equal amount of oxidation and reduction was takes place. That should be disturbed by the application of external current. When we apply external current, sometimes the reduction process becomes more, or sometimes oxidation process becomes more compared to the reduction. So this is the disturbance of the equilibrium between the oxidation and reduction process that we may call as polarization. Right? Is it clear? Electrode is said to be polarized when the equilibrium position is disturbed by the application of external current. By the application of external current, right? So if we can apply external current at the time the equilibrium position is disturbed, that we may called as electrode polarization. Electrode polarization, right? So then here one concept is not there, right? So I may explain that is the polarization, right? Or polarogram. Polarogram. So what is the polarogram, right? Simply, if we can give external voltage, right? If we give external voltage to the system, right? So that may produces current. We can plot the graph between current and voltage. If we can plot a graph between current and voltage, that may give this type of curve, right? That may give this type of curve. This we may call as polarogram. This curve we may call as polarogram, right? So here this is the limiting current, means where the maximum current will be there. So where the minimum current will be there, that is the residual current. So this is the limiting current, right? This is the residual current. The difference between the limiting current and residual current we may call as diffusion current. ID. ID means diffusion current. And this plot is known as polarogram, and the difference between the limiting current and residual current we may call as diffusion current. Diffusion current. So this is the concept may explain about the polarogram. Some polarography experiment will be there where we may utilize is dropping mercury electrode. So one of the electrode that we may use as dropping mercury electrode, right? So we will discuss about this dropping mercury electrode after this topic. So what that is decomposition potential, right? So simply by the application of voltage, current will be generates, right? So therefore, we can plot the graph of voltage versus current. We can get this type of sigmoid curve, right? So this we may call as polarogram. This highest current may called as limiting current, lowest current may called as residual current. The difference between the limiting current and residual current, this is the difference between the limiting current and residual current we may call as ID, that is the diffusion current. Diffusion current. So this ID may be helpful to explaining the further potentials of various over potential or decomposition potential. Two type of potentials will be there. One is the one is the decomposition potential, then other will be the over voltage or over potential. What is the over voltage? What is the decomposition potential? We'll see. Okay. So is it clear about the polarogram?
Yes, sir.
Yes. So now let's discuss about the decomposition potential. In the sentence itself will be there decomposition, right? So what was that means? Here see this diagram, right? Here HCl is an electrolyte solution. It may give H plus ions and Cl minus ions. When this will give these ions means by the application of external current or voltage. With the application of external voltage, right? External voltage, the electrolyte solution becomes converted into the ions. This process may be called as electrolysis process. When the continuous electrolysis process was carried out, right? So at that particular potential we may call as decomposition potential, where the continuous electrolysis process will be there, right? So where means at what potential the continuous electrolysis process should be done, that particular potential may called as decomposition potential. Decomposition potential. Just see the definition. The minimum amount of voltage is required to produce a continuous electrolysis of an electrolyte solution by application of external current is known as decomposition potential. Decomposition potential, right? The continuous electrolysis process was carried out by the application of external current, right? So therefore, the continuous electrolysis process should be carried out at what potential? At what potential the continuous electrolysis process is carried out, that we may call as decomposition potential. Decomposition potential. So just see here, one experimental setup will be there, right? So what it indicates, the experimental setup. So just to see, this is the experimental setup from which by the application of external current, the change in voltage we may occur, right? So just see here, A is an electrolyte solution. A is an electrolyte solution. In this electrolyte solution, we may dip two electrodes, that is the E and E dash. E and E dash, right? So what happens? Some people, somebody know saying no. Am I audible?
Yes, sir. Yes,
Yes,
sir.
sir.
Yes, sir.
Yes, sir.
Yes. Okay. Okay. Right. Fine. So simply just see the diagram, right? Here one electrolyte solution is there, that is A is an electrolyte solution in which two electrodes, the two electrodes E and E dash are the dipped in this electrolyte solution and connected to the voltmeter. Connected to
Sir?
the S.
Somewhat you can zoom the picture, sir.
This one?
Yeah, yes, sir.
Yeah,
Little
okay,
bit zoom.
I will. Right. So like that, if you are getting any disturbances, you may inform to me. I may rectify, right? So I can zoom this one. Right. Is it visible now?
Yes, sir.
Yes, sir.
Yes, fine. Right. So just see here, A is an electrolyte solution, right? This E and E dash are the electrodes. These are the electrodes. This is the one electrode and this is the other electrode. These electrodes will be dipped in electrolyte solution and connected to the voltmeter. Connected to the voltmeter. And also this voltmeter should be connected through a external battery. This is the battery, positive and negative, right? External battery followed by milliammeter and capacitor C, right? So here you people make it this arrow mark to the capacitor, right? So not in this place, okay, right? So which will be connected means the voltmeter should be connected with a capacitor followed by external battery and a milliammeter. So what this function of voltmeter and milliammeter, right? So the milliammeter may measure the current, right? May measures the current. So this V means that is may measures the voltage, right? The voltage should be controlled by the capacitor. This is the capacitor, right? With the help of variable capacitor, we can change every time voltage, right? When we apply different type of voltage, we can get different current, different type of the current. Or else with the help of external battery, we can apply the current to the system. This system means these two electrodes are there, electrolyte solution is there. One of the electrode may undergo oxidation, other will be undergo reduction. The redox reaction was takes place. At the time the potential will be developed. That potential we may measure through the voltmeter. Right? So these we may, by the application of different currents, we can get different voltage. Therefore, we can plot a graph of voltage versus current, right? So this is the current versus voltage. We can get the decomposition potential. At initial current, it will be slightly increases. The voltage will be slightly increases, that is from A to B. After some time, as we may increase the current, it may be suddenly increases. The voltage will be suddenly increases. Where the suddenly increasing voltage will be there, that we may call as decomposition potential. At particular current, the voltage will be suddenly increases, right? So that potential, where the suddenly increasing the potential will be there, that we may call as decomposition potential. That we may call as decomposition potential. So just we'll see after this experimental setup, we can get the voltage values and current values. If we can plot the graph, right? Therefore, we can get one diagram, right? So I will show this diagram, right? Just see this one. Right. So is it visible to you?
Yes, sir.
Yes, sir. Yes, sir.
Okay. So this is the diagram. So we can explain when the experimental setup will be there, we will get current and voltage values. We can plot the graph between current and voltage, right? So just see the voltage which can be measured in voltmeter, thus the voltage becomes known as decomposition potential. What we are saying, that means initially at low current, there is a slight increase in the voltage, right? So later on from B to C. Actually, this increment may be come through like this, right? So, but here the sudden jump in voltage will be there. At particular position, the sudden jump in voltage, right? So, where the sudden jump in voltage, that we may consider as the decomposition potential, right? Decomposition potential. The voltage which can be measured where the suddenly jump in the voltage, that becomes decomposition potential. So simply we can express this decomposition means continuous electrolysis process we want, right? For that we are applying external current, then the minimum voltage is required to get a continuous electrolysis of an electrolyte solution by the application of external current is known as decomposition potential. That can be measured through the some experimental setup from which at particular current the voltage will be suddenly increases. So where the suddenly increasing the voltage, that becomes a decomposition potential, right? So then coming to the over voltage, right? This concept you people may know, right? So what is the over voltage? First of all, just see the definition. Over voltage can be defined as the difference between the equilibrium potential and a actual potential. Equilibrium potential and actual potential of an electrolyte solution, which will be denoted as this one, simply we can produce this, right? If the hydrogen electrode will be there, whenever this hydrogen electrode should be combined with platinum, it will give standard reduction potential. Standard reduction potential is 0 volts, right? It will give standard reduction potential is 0 volts whenever hydrogen should be combined with platinum. See, this hydrogen electrode will be dipped in HCl solution and it should be combined with oxygen gas, right? Whenever it should be combined with oxygen gas, at that time this hydrogen may gives the potential that is 1.7 volts. The voltage was 1.7 volts, means without oxygen, the simply hydrogen electrode is combined with the platinum. At that time, the hydrogen electrode may give potential was 0 volts. When it combines with oxygen, at that time the hydrogen may gives voltage that is 1.7. The difference between these two, 1.7 minus 0, this is the voltage becomes known as over voltage. This is the over voltage or excess voltage, right? So whenever we may combine, right? So whenever we may combine hydrogen electrode with other gases, at that time it may give some difference in electrode, right? That electrode difference we may call as over voltage, right? So the equilibrium position means, right? The equilibrium position means actual position of hydrogen electrode is 0. The equilibrium position of hydrogen electrode is 1.7. What is the difference is there that we may call as over voltage. This over voltage can be explained with the help of concentration, explained with the help of concentration of an electrolyte solutions, right? So just see concentration over potential, right? Concentration over potential. So with the help of hydrogen electrode, we may express that, or also it should be clearly confirmed by concentration over potential. What is the concentration over potential? As we discussed yesterday, right? If you have to take any electrolyte solution, the metal should be dipped in that electrolyte solution, right? So what we are saying that the metal rod will be dipped in electrolyte solution. At that time, that metal may be involved in reactions, means based on their potential, the metal may involved in oxidation or metal may involved in reduction. When the metal is involved in oxidation, or else metal may act as anode. At anode, oxidation takes place. What is the oxidation of that metal? We may written as M gives rise to the M plus N electrons. M gives rise to the M plus N number of electrons. If metal lose one electron, that is M plus 1. Metal lose two electrons, that is M plus 2. Metal lose three electrons, that is M plus 3, like that, right? That is based on the nature of the metal. This is the oxidation reaction. Now apply the Nernst equation. That is E cell means metal is converted to the metal ion. E naught of metal is converted to the metal ion minus RT by NF ln of M plus N concentration means product concentration. These are the products. M plus N is the product concentration divided by reactant concentration, that is the M reactant concentration. M is the solid, metal is the solid, that's why we can eliminate this metal concentration. So therefore we can write this equation, that is E is equals to E naught minus RT by NF ln M plus N concentration. Just see, this is the E cell is directly proportional to the concentration of Mn plus. With respect to this, what we can say that as we increasing the Mn plus concentration, the EMF of the solution also increases, because directly proportionality will be there. So as directly proportionality of E cell with M plus N concentration, the metal will be involved in oxidation, means as going on the concentration of the Mn plus will be increases, right? So the E cell is directly proportional to the M plus N concentration. Simply we can say that as we increase the M plus N concentration, EMF of the cell becomes increases. As we decreasing the M plus N concentration, the EMF will be decreases when the metal will be involved in oxidation, and the same metal will be involved in reduction. Just see about that reduction reaction, right? So this is if the metal is acts as cathode. We don't know whether the metal is acts as anode or acts as cathode, means when we know that should be coupled with other electrode. The other electrode, two electrodes will be there. One electrode is having more reduction potential, that will undergo reduction. At the time, this metal may undergo oxidation. Or else the coupled metal reduction potential is less. At that time, the metal will be undergo reduction. So that is the thing. There is a two possibilities. Metal will be involved in oxidation and reductions. So the reduction of metal, that is M plus N plus N electrons, gives rise to the M. This is the reduction reaction. This is the reduction reaction. Now apply the Nernst equation to this reduction reaction. That is E cell is equals to E naught cell minus RT by NF ln activity of the product. Product means this is the M. Reactants means this is the M plus N. So that's why M divided by M plus N. The metal is a solid one. For solids, activity or concentration is 1. Therefore, 1 by Mn plus 1 by Mn plus. So therefore, see here, E cell is universally proportional to the M plus N concentration. When the reduction process of metal is takes place at that time, the EMF is inversely proportional to the M plus N. So therefore, we can say that as M plus N concentration will be increases, right? So as M plus N concentration will be increases, this is in denominator. As M plus N concentration will be increases, the EMF will be decreases. But in this previous case, as M plus N concentration increases, EMF also increases. That is happened in oxidation process. That is happened in oxidation. So right. So therefore, we can give conclusion for this, right? So what is the conclusion means? Just you can see this, right? The concentration over potential is obtained, right? The concentration over potential is obtained when as the EMF increases or decreases. As the EMF is increases or decreases, that is due to the increasing or decreasing the concentration of the metal ion. Sometimes metal ion concentration will be increases, at the time EMF will be increases. So if the metal ion will be decreases, even though EMF will be increases. So therefore the difference between that may consider as the concentration over potential, right? So whenever it should be involved in oxidation or it should be involved in reduction, right? So with respect to this, we can say that, right? So that is the concentration over potential can be depends on the nature of the M plus N. As the concentration of the M plus N will be increases, whether the metal is acts as or anode, at the time EMF will be increases. If that metal will be acts as cathode, the EMF will be decreases as increasing the M plus N concentration. So this is the difference between this increasing or decreasing, that is due to the increasing or decreasing the M plus N concentration, that we may consider as the concentration over potential. Concentration over potential, right? Is it clear? Simple
Yes, sir.
over potential means the difference between the equilibrium potential and actual potential, right? So the equilibrium potential will be high compared to actual potential. So that should be simply explained with the hydrogen electrode. The hydrogen electrode may combined with the platinum, that produces reduction potential is 0 volts. When it combines with some of the oxygens, at that time it may give some potential that is 1.7 volts. So the difference between that two, that is called over potential. That should be explained with the help of concentration of the metal ion, right? That is called concentration over potential, right? So then here one new concept will be there, that is concept of activity and activity coefficients in electrolytic solutions. What is that means? Concentration and activity. First we have to know about that what is activity and what is the concentration, right? So which may applicable for solutions if it is a ideal solution. If it is a ideal solution, we may express with concentration. For ideal solutions, we may express with concentration, that is in square bracket. But for non-ideal solutions, we already discussed this concept of ideal and non-ideal solutions in thermodynamics. Maybe you people may present or absent on that particular day. For non-ideal solutions, we may express with the activity, that is A. So therefore, activity A is equals to how we can say, how we can define means activity coefficient multiply with molarity. Activity coefficient multiply with molarity. This is the activity. Now we are going to find out the activity coefficient value. The activity coefficient value can be determined with the help of D by Haeckel. D by Haeckel. The Haeckel equation will be there. How we can determine the activity coefficient for electrolyte solution, whether it may be zero or positive or negative, how this may applicable for electrolyte solutions. These things we are going to discuss, right? So here one new concept will be there, that is a concept of activity. This should be applicable for non-ideal solutions, right? So simply here see, right? Right? The concept of activity and activity coefficients can be obtained for electrolyte solutions which are gets deviation from ideal behavior. That is the thing means whenever whenever the electrolyte solutions are deviating from ideal behavior, that may considered as non-ideal solutions. For non-ideal solutions, we may apply the concept of activity and activity coefficients, right? So then if the electrolyte solution becomes ideal solution, the chemical potential of these ideal solutions may be written as mu I is equals to mu I naught plus RT ln xi. Here xi is the mole fraction or else concentration of electrolyte solution. This is for ideal solutions, right? So what is the chemical potential? The chemical potential mu is equals to, you can write it as the change of free energy dou G by dou Ni, dou G by dou Ni at a constant temperature and pressure, at constant temperature and pressure. The change in free energy of the system with respect to the composition at a constant temperature and pressure, we may call as chemical potential. How this chemical potential could be changed for, right? This is the mu. The mu should be changed for ideal solutions means, that is mu I is equals to mu I naught plus RT ln xi. Instead of this xi, if we can write AI, this is the same equation is applicable for non-ideal solutions. Instead of xi means concentration, if we can use activity, that equation can be applicable for non-ideal solutions, or else those solutions which are deviating from the ideal behavior. For that all solutions may applicable this equation, that is mu I is equals to mu I naught plus RT ln xi. So therefore, with the help of this activity and activity coefficient and also mean ionic activity, that all should be determined with the help of concept of D by Haeckel theory, right? So just see, right? Here is the equation. This is for non-ideal solutions. Mu is equals to mu I is equals to mu I naught plus RT ln AI. Here xi be the for ideal solutions, AI be the non-ideal solutions, right? So therefore, the activity can be defined as, right? This is the activity of an electrolyte solution that should be defined as the product of activity coefficients and molarity. So therefore, A is equals to gamma into M. A is equals to gamma into M. A for activity, gamma for activity coefficient, then M per, this is M, not mu. This is M per molarity.
Molarity.
Right? So this is the activity coefficient we are going to determine with the help of application of concept of D by Haeckel theory. So what is D by Haeckel theory? How we will get gamma value? We'll see. Right? It's a very easiest concept, easily understandable concept of D by Haeckel. Right? So what is the D by Haeckel? We'll see. Right. Then here, if that activity concept may applicable for only one ion, that is a cation represented with positive charge, A plus is equals to gamma plus and M plus, means activity coefficient plus activity coefficient for cation, concentration for cation, or for else for anion, A minus is equals to gamma minus into M minus. Therefore, the electrolyte solution, whatever is the electrolyte solution, you may consider, for example, HCl is an electrolyte solution which may containing H plus and Cl minus, right? H plus means positive ion, that is cation, and both ions are present in electrolyte solution. That's why we can written as the activity of this electrolyte solution as the product of activity of the cation and activity of the anion. So we know that activity of the cation gamma plus M plus. We know that activity of anion gamma minus M minus. Therefore, AI activity is equals to A plus or minus is equals to gamma plus or minus and M plus or minus. Just you people make it this. This is all M only. Sometimes this may written as like mu, but you may write M only. That is a concentration only, right? So just make it difference. Here it will be seeing like mu, but that is not mu. This is the M only. Yes, understand?
Yes, sir.
Yes, sir.
Yes, this is all M only, not mu.
Okay, sir.
Okay.
Yes, sir. Okay, sir.
That is the student mistake only. He may understand that is mu, right? So, but that is all M's only. Whenever gamma is there, the adjacent of gamma becomes M only. You have to remember. Okay. Right. Therefore, here finally we'll get A plus or minus is equals to what? A plus or minus is equals to gamma plus or minus into M plus or minus.
Yep.
Therefore, with respect to this, we can written as gamma plus or minus is equals to what we can write? A plus or minus. A plus or minus divided by M plus or
M plus or minus.
right. These gamma plus or minus we may called as mean ionic activity coefficient. The gamma plus or minus we may call as mean ionic activity coefficient. This mean ionic activity coefficient can be determined by the application of D by Haeckel theory. What is the D by Haeckel theory? How this should be applicable for electrolyte solutions? From that, how we can determine the gamma plus or minus? That is the mean activity coefficient for electrolyte solutions. That is the thing we are going to discuss. Right? Is it clear?
Yes, sir. Yes, sir.
Yes, sir.
Yes. Okay. Right. So just we'll see. So nice concept of D by Haeckel. Just you people may concentrate little bit, right? So I can give simple and clear information about the D by Haeckel, right? We said that just some small concept is there. That is the mean ionic activity coefficient. We have to know that mean ionic activity coefficient. Then how can be determined with the help of application of D by Haeckel theory, right? So that we'll see, right? The mean ionic activity coefficient of an electrolyte solution depends on activity and concentration, because Just previously we wrote that gamma plus or minus is equals to A plus or minus divided by M plus or minus A plus or minus divided by M plus or minus. This activity coefficient of an electrolyte solutions depends on activity and concentration. Activity and concentration. So if we take one example, that is Ma is the electrolyte solution, M is the cation, A is the anion. So therefore M plus and A minus. M, the number of moles that is denoted with the X, right? Here A number of moles that is denoted with Y. So therefore we can write equilibrium constant, right? The equilibrium constant for this reaction. What is the equilibrium constant? The product concentration by reactant concentrations. Product concentration by reactant concentrations. Here, what is the product? That is M plus and A minus. Here, minus will be missed. A minus divided by Ma concentration. So this M plus we may express with activity. Activity of M plus, activity of A minus. This is not Y minus, A minus. Activity of A minus. Some little bit corrections are there. You may focus, right? Here we are expressing M plus means this is A minus. This is not AM plus AY. This is the A minus into AM plus. Okay. So divided by activity of MA. Activity of MA. Right. So therefore, these should be simplified. So finally we can get A plus or minus is equals to A plus or minus is equals to gamma plus or minus of X plus Y into M plus or minus of X plus Y. M plus or minus of X plus Y. So therefore we can simplify gamma plus or minus of X plus Y is equals to A plus or minus by M plus or minus of X plus Y. Here this gamma plus or minus is called as mean ionic activity coefficient. So that can be determined with the help of application of D by Haeckel theory. So then what is the D by Haeckel theory? How we can determine that activity coefficient, right? So that we'll see. Okay, right. Just wait. Right. So just one, you people may wait 1 minute. I want to drink some water. Right. So just please wait and just read the sentences. Okay. D by Haeckel. I can reduce this one. So just little bit. Right. So these are the two papers, right? Some more. Right. So these are the two papers are there. Just you people may zoom and you can read these sentences. I'll be back in 1 minute. Yes, back to the class. Are you there?
Yes,
sir.
sir.
Yes. Okay. So just a little bit, I will zoom out, zoom in. Right. Let's see what is the D by Haeckel theory. Some assumptions are there, right? Some assumptions are there with respect to this. They may give some equations. That equations are applicable to mean ionic activity coefficient, right? So what are those? Just we'll see. Just see the first one. The strength of electrolyte are completely, right, dissociates into ions. Right. See here some mistake is there. Here not the strength, strong electrolytes. The strong here you may make it as strong. Strong electrolytes are completely dissociates into the ions. Strong electrolytes like HCl will be there. That HCl may gives completely dissociate into the ion. That's why it may considered as the strong, right? So the strong electrolytes are completely dissociates into the ions. The weak electrolytes are partially dissociates into the ions. This is the simple two things you people know, that is right. So whenever it is a strong electrolyte, that may gives complete 100% ions. When it is a weak electrolyte, that may gives a partial number of ions, right? So strong electrolyte completely into the ions, weak electrolyte, right? One more point for strong electrolytes. The strong electrolyte solution having the high dielectric constant value. This is not a disk, right? This is the die only. So some mistakes are there. You people may recognize. So then you make it correction, right? So here this is the die, not disk. This is the die only. Means strong electrolytes are having high dielectric constant values. This is the not this. This is the only die. Due to the strong electrostatic attractions between the ions is small, right? See, this is HCl, H plus and Cl minus is visible to you, right? Whenever H plus and Cl minus formation is there, complete H plus and Cl minus formation means the interaction between these two H plus and Cl minus becomes very small. That is electrostatic attractions. ఒకవేళ ఎలక్ట్రోస్టాటిక్ అట్రాక్షన్స్ స్ట్రాంగ్ ఉన్నాయనుకో అవి అయాన్స్ గా విడిపోవు, రైట్? సో దట్ ఈస్ హ్యాపెండ్ ఇన్ కేస్ ఆఫ్ weak acids. A weak electrostatic attraction or a small electrostatic attraction may give high dielectric constant values. That is happened in case of strong electrolytes. If it is a weak electrolyte will be there, the attraction between the positive ion and negative ion becomes so large. A large attraction will be there. That's why cannot be converted into the ions. That's why partial ionization was takes place, right? So carefully remember these things, or you may read out carefully, right? So what is that means? First 2 points is very simple. The second and the third and fourth points are again I am explained. The strong electrolytic solutions containing high dielectric constant values, that is due to the low electrostatic attractions between the ions. In case of weak electrolytes or dilute solutions, the electrostatic attractions between the ions is strong, which causes low dielectric constant values. Okay, strong means that will give completely ions. So this is the positive ion and negative ion. The attraction between these two ions is very small, therefore this may gives high dielectric constant values. Then the force of attraction between these ions is directly proportional to the product of charge of ions and indirectly proportional to the distance, square of the distance between them. So this is according to the Newton's second law. So we people know second law of Newton, right? So that is what F is equals to Q1 Q2 by R square. This is that. Means we are saying that some force of attraction which will be acting in between the cation and anion, that force of attraction is directly proportional to the product of charges on cation and anion and inversely proportional to the square of the distance between them. So therefore, the electrolyte solution, each ion surrounded with what is here we may convey. If cation is there, each ion that should be surrounded with many number of negative ions. ఒక్క పాజిటివ్ అయాన్ మెనీ నంబర్ ఆఫ్ నెగటివ్ అయాన్స్ తోటి సరౌండెడ్ అయి ఉంటది, రైట్? ఆర్ ఎల్స్ ఇఫ్ వన్ నెగటివ్ అయాన్ దట్ షుడ్ బి సరౌండెడ్ విత్ మెనీ నంబర్ ఆఫ్ positive ions in symmetrical manner. So that is the point of number 7. So what is that means? Two ions are there in an electrolyte solution. One ion is surrounded with opposite charged ions in a symmetrical manner. Opposite charged ions in symmetrical manner, right? See, each ion surrounded with many number of opposite charged ions in symmetrical manner. When we applied electric field, the symmetric manner is disappear. ఒక్క ion దాని చుట్టూ opposite ions. So the middle ion may called as central ion that should be surrounded with many number of opposite charged ions. That is in symmetrical manner. When the symmetrical manner will be disappears means by the application of external current, right, or electric field. By the application of external electric field, that environment may be disappear. That should be explained with the help of right term, that is interionic effect, right? What is the term? Interionic effect. Interionic means between the two ions. Intro means same. Inter means different. Two different ions may exhibit some effect. So with the help of that, the Debye and Haeckel may explain the concept for electrolyte solutions. What are those three effects means? Asymmetric effect and electrophoric effect. One is the effect is called what? Asymmetric effect. The other will be electrophoretic effect. Electrophoretic effect. So this asymmetric effect may sometimes called as relaxation effect. Relaxation effect. What is the asymmetric effect? We'll see. Okay. So is it understandable of assumptions of D by Haeckel? Simple thing, right? Strong electrolytes, weak electrolytes. How they may have attractions between the ions. Then the force of attraction can be directly proportional to the Q1, Q2 by R square. Then one ion that should be surrounded with many number of opposite charged ions. Their interionic effect will be developed. The term of interion effect can be explained with the help of two effects. One is the asymmetric effect and other with the electrophoric effect. What is the asymmetric effect? We are going to see. Okay. So this is the asymmetric effect, right? So simply we said that this is the positive ion. This positive ion may surrounded with many number of negative ions. The positive ion that may be surrounded with many number of negative ions in a symmetrical environment or symmetrical atmosphere. When we apply electric field, this symmetrical manner may be disappear. That is asymmetrical environment, because electric field means positive pole and negative pole. The positive ion will be moved towards the negative pole. All the negative ions are moved towards the positive pole. So due to this, the symmetrical environment may be disappear. The symmetrical environment may be disappear, right? So that is called asymmetric effect. Asymmetric effect. So what is the relaxation means? Whenever this ion will be moves towards the central positive ion moves towards the negative pole, right? The central positive ion which will be moved towards negative pole, the remaining negative ions are restricted, means which may control the moment of the positive ion, right? So the remaining negative ions which may control the moment of the negative ion, moment of the positive ion that may move towards the negative pole. That retarding of the speed of the central positive ion may called as relaxation or asymmetric effect, right? So simply here what will happen means the positive ion which will be simply moved towards negative pole, but the speed of the positive ion should be controlled by negative ions, right? So that is the effect is called asymmetric effect. Asymmetric effect. Is it clear?
Yes, sir.
Yes, sir.
Yes. Simple and I may convey in Telugu, so that is very easy to understandable, right? So ఏమైతుంటది, one person may surrounded with many number of your friends, right? You want to go to one job, right? So some of your friends may stop you. So this is not suitable to you, or some other reasons, right? So your process may become so slow. So that is the thing, right? Means you are influenced by your friends. So like that, this positive central ion is influenced by this negative ions. The mobility of this central ion becomes very less. That is due to the attracting of the negative ions, right? So that is the process we may call as asymmetric effect. Asymmetric effect, right? So this is the same matter will be there. You may read out later, right? So then coming to the electrophoretic effect, right? Electrophoretic effect. Here only matter will be there. So what is that matter means, right? We'll see. That is depending on the size, right? For example, central positive ion will be there, right? which may be present in the presence of any solvent, that is the water molecule is a solvent, means which will be surrounded with water molecules, right? All water molecules, right? So in addition to the asymmetric effect, the mobility of the central ion is decreases due to the solvent molecules are surrounded with the central ion. These solvent molecules was what? Water. If water is used as an solvent, right? Water is used as an solvent, right? Used as the solvent. These all water molecules are surrounded the central positive ion or maybe central negative ion. Therefore, at that time, the mobility of the central metal ion may decreases due to the surface water molecules. Even that effect may called as electrophoric effect. Previously in asymmetric, we don't discuss about solvent molecules. If is there any solvent molecule, even that will be affected the moment of the central ion, that may be either positive ion or negative ion, right? So we'll see. So after this, just one sentence will be there. So that is right. So if the solvent is water molecule, many number of hydrated molecules, right? Many number of hydrated molecules are surrounded with the central ion, which leads to the retarding the mobility of the central ion, which makes towards their opposite side, opposite pole. So therefore, which causes decreasing the electrical conductance of an electrolyte solution. This phenomenon is known as electrophoretic effect. One is the what? With the help of electric field, the mobility of the central ion will be decreases. In other case, with the help of solvent, the mobility of the central ion will be decreases, right? So these are the D by Haeckel assumptions, right? So these are the D by Haeckel assumptions. With the help of this D by Haeckel assumptions, D by Haeckel may derived one equation, that is D by Haeckel limiting law, right? So then this D by Haeckel limiting law is applicable for strong electrolyte solutions also, that may consider as the extended D by Haeckel limiting law. Later on, Onsager was added to the D by Haeckel. They may produce this one equation, that is D by Haeckel Onsager equation, which will be applicable for all electrolytes, right? All electrolyte solutions. So this is the assumptions of D by Haeckel asymmetric effect and electrophoretic effect, right? So then the some other equations of D by Haeckel that we will discuss in the next class. Yes. So today the concepts we covered that, right? So one is electrode polarization, decomposition potential, then over voltage, concentration, over potential, then concept of activity and activity coefficients, then mean ionic activity. So then D by and Haeckel assumptions and D by and Haeckel theory, right? So further, which will may expand D by Haeckel limiting law, extended D by Haeckel limiting law. So then D by Haeckel Onsager equation. So later on, two equations will be there that are Ilkovic equation and fixed first law of diffusion, right? So some other topics are there. We will cover in the next class, right? Yes. Is there any problems? You may now talk to me.
Excuse me, sir.
Yes,
What
ma'am.
about the notes? You said you will be giving the notes, but we haven't received the notes yet.
Yeah. I'm not at send, right? So right now I will send. Okay.
You will send on Telegram or WhatsApp group?
M.Sc. counselors group, WhatsApp group is there, na? You are in WhatsApp group?
Yes, sir. Yes, sir.
Yes, sir. We are in
Telegram group.
M.Sc. counselors, this is the Telegram group.
Yes, sir.
Yes, sir. The
Telegram group.
main group is Telegram with Kodeshwar, sir. You made on Telegram.
Yeah, okay. So right now, immediately I will send these notes, right?
Okay,
See,
sir. Thank you.
వాట్సాప్ లో కూడా పంపండి సార్
Huh?
వాట్సాప్ లో కూడా పంపండి సార్ గ్రూప్ లో
వాట్సాప్ గ్రూప్ ఏమనుంది మరి?
Sir,
So you send on Telegram, we will forward it on WhatsApp.
Yeah. Otherwise, any one person may put a message to me personally. I may share to you. You may post in the WhatsApp group, and I will share in Telegram group.
Yes. Okay, sir.
Okay, ma. Fine. Right.
Sir, WhatsApp group లో ఎవరం లేం సార్, తెలియదు అసలు.
Okay. I may send to any one person. He may take care, right?
ఓకే సార్.
So you may send in a Telegram group or so whichever group is there. You may
Send on
post it.
Telegram group, sir.
Okay.
Telegram.
Okay, sure. Right. Fine. I am going to conclude the meeting. Right.